So yeah. Talking about functions today, and we'll define what a function is, right? So a function, I'm getting a little bit there for us. There we go. Okay, a function from a set A to a set B. So the idea here is that a function, right, is a relationship. It's a specific kind of relationship that shows up. There's like a more general term, right? I think we can talk about like a relation between two things, but then we have a function is a specific kind of relation, and it takes something from a set and it relates two things from two different sets. Okay, typically for math, right, those are numbers, right, or sets of numbers, right, like the rational numbers or the integers or the real numbers, stuff like that. Okay, but a function from a set A to a set B is a relation, so it's a kind of relation that assigns each element x from set A to one element y in set B. Okay, whoops. There you go. Zoom out one. Okay. Right, this is something you guys have been talking about probably since elementary school, in one form or another. Okay, that idea, that concept. So we're seeing it one more time here. Okay. Remember, an element, right, is an individual member, an individual part of a set. Right, you have a set, which is a group of things. One part from that set is called an element. So it's x from set A, and then an element y from set B. Okay. And so it relates, it assigns an element x from set A to one element y in set B. Or in like kind of like layman's terms, or like every x goes to one y. Right? That's a kind of easy way to think about it, right? Every x goes to one y. In a relation, which is a more like general kind of way to relate to things, it doesn't have to be that way. Okay? A relation is just like literally something that assigns an element from x, or an element from set A to an element from set B, or to elements from set B, or set B and stuff like that. Okay, this is a more specific version of a relation where it's every element from set A gets assigned to one element in set B. Okay, so that's what a function is. But of course, for our purposes, we're talking about math and like numbers and things, and so we want to be able to identify functions, right? So we're going to do function testing to determine is something a function or not. Okay, so one way to do this, I guess I'll call this one like algebraically. Okay. We just, again, all we're doing is just check to see that each x is assigned to one y. So again, check to see that each x is assigned to one y. That's something basically just like, in other words, see that this thing fits the definition. All right, see that this thing fits the definition, right? So for example here, okay, we'll ask the question, is it a function? Is the relation a function? Okay. And then I'll come up with a relation here. So let's just say, and again, sometimes it can be something as simple as like a set of numbers here, right? A set of ordered pairs. So -1, 6, 2, 5, 0, 9, 3, 5. Okay. So this illustrates a couple things here, right? First of all, we know what set A is. Set A is going to be the numbers -1, 2, 0, and 3, right? Those are our x's. Set B here would be our y's, 6, 5, 9, and 5 as well. So really 6, 9, and 5, right? And then this is also showing these ordered pairs, right? They're showing then not only the set A and set B, but they're also showing the relationship. -1 relates to 6. 2 is paired or relates to 5, 0, and 9, 3, and 5. Again, okay? Does this demonstrate a function? Does every x value go to one y value? Yeah, so -1 goes to 6, right? Okay, 2 goes to 5, 0 goes to 9, 3 goes to 5. Is it okay that 2 goes to 5 and then 3 goes to 5? Yes, it is okay. Yes, it's okay. That's all right. Okay? We don't care how many y's go to a single x. We care how many x's go to a y value. Okay? How many x's are paired with that y value? Okay? Every x should go to one y value there. All right, so let's try another one here. Let's take a look at, that was the first one. We'll do here one here as well. How about like 6, -2, 9, 3, 8, 2, 6, 1. Is that going to be a function? No. Okay, and how does it fail? Where does it fail specifically?
6 is paired up with -2 and 1.
Exactly right. 6 is paired with the -2, and 6 is paired with the 1. And so, no. Okay, 6 goes with the -2, 6 goes with the 1. So, x goes to two different y values. Okay, x goes to two different y values there. So that's part of the issue there. Okay. Cool. All right, so that's that. All right, that's pretty straightforward. We'll also talk about graphically too, which is maybe the more common way that we do this. Well, I guess you can kind of do it both ways, but it's quick because you can see it visually. All right, and this is from the vertical line test, right? Okay, what we know is the vertical line test. So, and there's not necessarily I don't have a very elegant. I don't have a very elegant way of saying this, so I'm going to try and write it out as best I can here. But if a vertical line passing any part of the graph of the relation intersects more than once. Okay, so it's a vertical line test. If a vertical line passing any part of the graph of the relation intersects more than once, then the relation is not a function. Okay. So when we graph something, we are again establishing a relationship. Okay. When we graph something in like the coordinate plane and stuff like that, we're saying these x's match with these y's. They create points, and then those points all together create this like smooth, continuous, this curve or whatever kind of thing, right? That's what we see when we do a graph. Of course, we can just also have points as our graphs as well. But the idea is, right, if I go to like think about the coordinate plane here, and the point like 6, -2, and 6, -1. So again, just hypothetically here, 1, 2, 3, 4, 5, 6, 1, -1, and -2. So 6, 1, well, that would be the point 6, 1 there, right? And then 6, -2, that would be the point 6, -2. Okay. And so you can see the issue here, right? And of course, there's other points, but we don't care about those. They're fine, right? These two, they're the problem. And why are the problem here in this one, right? Well, this x value of 6 is being paired with two different y values, right? And that causes this to fail, because now if I draw a vertical line through that relation, it's hitting both those points. And that causes this thing to not be a function. We can't define it as a function. Okay? So that's kind of the relationship there, right? You can see the same x value going to two different y values causes the vertical line test to fail, right? So there's that, right? And it's for that reason then that, for example, is the graph of a circle a function? No, right? And we talked about that kind of already. You can see it show up here in another way too. Let me just show you. Let's say we have a circle that's like x squared plus y minus 2 squared equals 16. All right. If we wanted to graph this, we need to solve for y. So I'll subtract x squared from both sides. Okay, square root both sides. Okay, and because we're in an equation setting here, I need to put a plus or minus in there. All right, and I'll go ahead and add the 2 over. Okay, and so you can see here how you can also see kind of algebraically. All right, you mean everyone in here can picture a circle, right? You've known circles since probably before you were in school, right? And so it's like, and then you can just picture, can I draw a vertical line through it? Will it hit more than once? Yes, right? But you can also see it here algebraically too, right? Imagine plugging in a particular x value here. Let's just say an x value of 1, right? If I plug an x value of 1 in, 1 squared is 1, 16 minus 1 is 15. I'm going to take the square root of 15, and my y value that matches with that is going to be 2 plus the square root of 15 and 2 minus the square root of 15, right? And so there we can see right away, a single x value of like 1 is going to match, is going to pair up, according to this rule, is going to pair up to 2 different y values, so we can also see it there algebraically as well, okay, in the very equation when we solve it for y and stuff, okay? So obviously, we knew this already, but I'll just put that here for emphasis. All right, so you can see it in the equation too. All right, questions on any of that? All right, so let's take a look at then our graphs of basic functions, okay? Something you guys spent like all of Algebra 2 developing, right? It seemed like, when I taught Algebra 2 at least, it seemed like every unit there was some new parent function to learn and then to apply all those different transformations to. And so we're going to re-summarize some of those important parent functions, right? And so then also we're going to go over a few more of those transformations just to make sure we're okay with those. Again, because some of us have been further away from Algebra 2 than others. And that's that, okay? So we'll cover up to, we're not going to do sine and cosine today. That's going to be later, so something to look forward to, all right? Everybody loves trig, right? Yep, okay, I'll take your silence as a yes. And so we're going to do these 6 right here, okay? We're going to do these 6 right here right now. Okay, so the identity function, that is just literally the function f of x equals x, right? Or y equals x if you like. And we'll just kind of sketch the graph of this. I'm going to do like a very quick and dirty sketch. I'm not even going to like put coordinates down or anything like that. We all know what the line y equals x looks like, right? You know what that looks like. Slope is 1, y-intercept is 0. Okay. I'm going to also, let's see, do I want to? Yeah, I'll go ahead and talk about it here. Okay, we're going to talk more about domain and range a little bit later too, but I'm going to go ahead and talk about it here too. What would the domain, that is, what are all the possible x values that we could plug in to this function and be okay? So let's Ryan, why don't you go ahead there, Ryan?
It's negative infinity to infinity.
Very good. I like that you described it that way. Yeah, negative infinity to infinity. Yep. Oops, Mr. Wid. Okay. So a couple different ways you can describe that interval that Ryan just described, right? You can say parenthesis, negative infinity to infinity, and that's supposed to be a parenthesis there, not a square bracket. Okay. Alternatively, if you like, you can say like all real numbers, and you can even use a symbol for real numbers if you want to, or you can say all x values, or you can say all you could like use an inequality, negative infinity less than x less than infinity too. It's really up to you what you're comfortable with. My recommendation, right, is that you get comfortable with the interval notation, but I'll accept it, kind of anyway, as long as the directions aren't specific about it. Okay. So, anywho, that was a long piece there. And then, so what would the range then be? Hayden, you want to say what the range is? Also negative infinity to infinity. Okay. Again, just by looking at the graph here, you can see, again, the domain deals with x values, range deals with y values. We're going to go, keep going up and up and up. So we're going to hit all these positive y values and going to go down and down and down. So we're going to hit, again, all those negative y values too. Good. All right. Absolute value function. That is f of x equals the absolute value of x. Actually, no, I'll zoom in. Something like that. Okay. Okay. Absolute value function, a little bit more interesting. Okay, looks like that. Okay. What is the domain for this function? What will the domain for this function be? Go ahead, Cooper.
Negative
Negative infinity to a positive infinity, exactly right. Cooper, can we say the same thing about the range? No. Okay, so then what is the range then?
0, negative infinity is 0, I think.
So be careful. What's the lowest y value we can get to? Like 0. So it starts at 0, and then
0 to infinity.
there it goes, to infinity. Yep, to infinity, right? And we'll include the 0 there too, okay? Like that, right? Easy peasy, all right? So then the next one we'll look at is the square root function, square root of x. Okay, and we'll get a little picture of this. So this one I'm going to maybe take a little bit more time with because we're maybe less familiar with this one. So 1, 2, 3, 4. Okay, we'll do like 1, 2, like that. Okay, so what's the lowest x value that we can plug into this thing? 0, right? We can take the square root of 0. What is the square root of 0? 0, right? It is a perfect square, right? And so we have 0, 0. Okay, and then we can try, 1. We can put 1 in. Square root of 1 is 1, so we'll do 1, 1. And then 4 we can plug in, right? Square root of 4 is 2. Just like that. And so our curve's going to look something like that. Okay. It will continue to increase, but it's going to like decreasingly increase. Okay, it's not going to increase by the same amount each time there. Okay. And the shape for this is going to be similar to like a 4th root, a 6th root, an 8th root, a 10th root. Any even-powered roots, we're going to run into the same issue because we can't take the square root of a negative number. It's imaginary, right? And I think we're going to deal a little bit with imaginary numbers. We might skip imaginary numbers altogether. I forget now. I'll have to take a look back there. We'll see. We'll get there when we cross it. We'll cross that bridge when we get there, I guess. But anyway, so the domain here is going to be from 0. Actually, it should be. Oh, is it open? Yeah. Okay. So 0, 2, and then what's our upper limit on the domain there? Infinity. That's right. We can take the square root of, or lots of big numbers if we wanted to. Okie dokie. That's 10. All right, and then what about the range for this thing then? What's it going to be? What's the range for this? Steve? Say again? 0 to infinity as well. Exactly right. Okay, very good. Very good. Oh, there you go. That's why. Okay. So yes, also 0 inclusive to infinity, right? Right. So we're going to use that square bracket because we include the 0, and then to infinity we don't include infinity, right? All right, let's try another one here. The squaring function, which is quadratic, or however you want to call it there, f of x equals x squared. Alrighty. And again, I'm not going to spend too much. You guys kind of, know what this is like, right? It's a parabola. You guys have been working with these since at least Algebra 1. Domain here, all real numbers. So we'll say negative infinity to infinity. And then the range, though, is that also all real numbers? Nope. It is what? Anybody? 0 to infinity, right? Including the 0 to infinity. Scoot up here and we'll get the cubing, and then the rational function. Rational is going to be 1 over x. But then again, we'll do cubic. So x to the 3rd. Okay, now it's something like this. Okay, roughly, again, I'm not. It's more the shape. Okay, domain here. Okay, we can cube positive and negative numbers, no problem. So it's negative infinity to infinity. All right, and then the range. It's also all real numbers, right? It's also all real numbers. Unlike x squared, right? If you square a negative number, it's going to be positive. That's why over here where you have negative x values, you still end up with positive y values, right, above the x-axis. Here, right, when we have negative x values, our y values are also going to be negative, because a negative times a negative times a negative is also negative, so you end up down here. in the third quadrant, right? And then with positive x values and with positive y values. Everywhere increasing. All right. And last one, rational function f of x equals 1 over x. Okay. And this one looks a little bit funky too, right? This one's a little bit funky, probably the funkiest of all of them. All right. What is the domain for this function? Is it all real numbers? Can we put in any x value there and have no problems? So, what do we say? Ramike. Yeah, exactly right. We have to exclude 0 there. And in interval notation, it would look something like that, right? In words, right, if you were just going to write it out in words, you could say all real numbers except x equals 0, right? That's an easy way to exclude it, right? All real numbers except x equals 0. If you wanted to say it in inequalities, you'd say like x less than 0 or x greater than 0, like those kind of things. Okay, or and x greater than 0. Anyway. All right, the range. Well, this is a little bit trickier to show, but I'll go ahead and draw the graph now. Are we going to hit every y value here? Is every y value included in the range? Is it all real numbers? No? So, yeah, see? Again, exactly right. Now, this one's a little bit harder to see, right? Or maybe not. Maybe it's not for you. But, I think it's kind of an easy argument to make, right? We know as math students, right, you're not supposed to divide by 0, right? You're not supposed to do it. So it makes sense here that we say, okay, well, x can't be 0 then because it would be 1 divided by 0. That would not, you wouldn't be able to equal 0. Or you can't have x equal 0 because you're dividing by 0, right? That's bad. And we'll explain I'll try to explain a little bit more later about why it's bad that we don't want to, why we don't divide by 0. Maybe you've seen it before, but just an idea about why it's, what we call undefined, okay? For the range, though, it's maybe a little bit harder to see. How can we kind of convince ourselves here that the y value will never be 0? Well, one way I can maybe try and convince you here is that we've got this 1 over x, which is a fraction, right? A fraction is only ever equal to 0. Okay, so a fraction only ever equals 0 when what part of that fraction is 0? The numerator, right? Our numerator here is always what? 1. So it can never be 0. It's always 1. And so we won't ever have a possibility for y value to be 0 there. Okay, y, or f of x, is 1 over a number. Since that's always 1 in the numerator, this thing can never equal 0, okay? Or it will never equal 0 exactly, right? We can approach it, but we can't get there. And so the idea is then that this the range is not excludes 0. Okay, so flip over to the back real quick, and we're going to look at some transformations. All right, and then we'll be done here. All right. And then we will be done. Okay. So, and again, I'm going to break these transformations down and make my transformations a little bit simpler than maybe what you guys had to cover back in Algebra 2, right? In Algebra 2, you guys were like, man, I just keep beating up this poor clipboard here. Back in Algebra 2, you were responsible for maybe like a few more complicated kind of calculations maybe when it came to those transformations. We'll keep it a little more simple just because we don't need to, go too crazy there. But let me show you what I'm talking about. Right? So for example, right? Okay. And for these, we're going to assume that the number c is greater than 0. Okay? Assume that c is greater than 0. So if we take our function f of x, all right, and that means then any, right? These are all defined as f of x's, right? If we take one of those functions, f of x, and we add that positive c to it, how will that transform the graph from the original parent to f of x plus c? How does that transform the graph? What does that do? Ramika, you want to go? Okay, since it's a positive c, specifically which direction then? Up. And then up how much? more than 0, well, and they'll just C, exactly, whatever C is, right, it'll be that much. So yeah, in this case, since C is greater than 0, more than 0, but specifically, it'll move up C. So yeah, shift up, or translation up C units, right, if we want to use terms from geometry. A translation, right, is when we shift things. Okay? So then if that's the case, right, then likewise, if we see f of x minus c, how would we expect things to move? Down c units. Bless you. Okay, let's move that c though. Now let's do f of x plus c inside. This is a little bit trickier here. If I move the c inside with x like that, how does that shift things now? f of x plus c. Pardon?
Shift it to the left C.
Very good. Okay, counterintuitive to what we might think. We might, oh, plus c, that means it's going to go right, because plus is like a positive direction. Not so. It's the opposite of what we might expect here. This is a shift left c, oh goodness, c units. Okay, and so then, since we're all very good with our opposites here, right, then f of the quantity x minus c is going to shift things which direction? Right. C units. Okay. How about negative f of x? Put a minus sign in front of our function. Okay, the opposite. Yep, right.
Flip it upside down.
Okay, flip it, yes. Can you be more specific? Over what?
The x-axis.
The x-axis, very good, yes. I'm going to use the word reflect, but a flip is fine. Reflect over the x-axis. Okay, which again shouldn't surprise us here. We're going to take some x value, like imagine taking any random x value, plugging it into our function. It's going to give us our normal y value, but then the exact opposite of it because there's a negative in front. Okay, so if you throw a negative in front like that, it's going to give you the normal y value for that function, and then flip it over. So from a positive y to a negative y, from negative y to a positive y, that's reflecting over the x-axis there. Okay, and then to reflect over the y-axis, we'll do f of negative x, like that. And that is a reflection over the y-axis. Okay, so we're going to take a look at 2 sketches here real quick, and then I'll have you guys try one, and then we're done. All right, so we're just going to sketch a few things. So, for example here, we're going to use some of these transformations. Okay, to sketch. So sketch. And this is the purpose of knowing this information, is that rather than having to always go to our graphing calculators because, you know, there might be non-calculator portions and stuff like that, rather than going to our graphing calculators and giving away the information, knowing this information can help us graph things a little bit easier, right? So for example, as a quick sketch or something like that. So for example, g of x equals negative x cubed minus 5. Okay. So our parent function is going to be that cubic. All right, so our parent function is the cubic there. But that minus 5 is telling us to do what? Yeah, right. So are we supposed to move it to the left 5, or is it supposed to be like a down 5? Which one is it? It's going to be a down, okay, right. And the reason for that is because where is the minus 5? It's on the outside of the function, right? Our original function is x cubed, and then we're subtracting the 5, okay, it's on the outside. If it was the quantity x minus 5 cubed, like that, that's a shift right. Right 5. So this is right 5, but this one here is down 5. Okay, so right 5, the minus 5 is in with the x. Down 5, the minus 5 is outside. Okay, outside of the cube. What else is going to be happening, though, in this graph? Not only shifting down 5, what else are we going to experience? A reflection. Yep, reflection. Okay, so you can reflect over the x-axis first and then shift it down. That's what I'd recommend you do there. Reflect first and then shift. Okay, so we'll go down 1, 2, 3, 4, 5. Okay, so we're shifting from the origin which is kind of like where our, you know, like I guess we'll call that the center point. I want to call it a vertex because it's not really a vertex, but that central point there. We're going to shift that down 5 to right here. And that's going kind of like up from left to right. We're going to go down from left to right. So again, just something looks like that. Okay. Again, I'm not too worried about your precision there. If you want to, you could absolutely make an XY chart. You know, and then just get your points and plot it if you want to make it like super accurate. But I'm not so worried about that. I'm just worried about getting you guys getting a quick sketch to know what it kind of looks like. So that kind of thing is fine right there. All right, let's try another one here. How about g of x equals negative x minus 2 squared plus 1? Okay, so. Okay, so Kat, can you describe here what kind of transformations we see?
Well, the plus 1 would mean it's like going up 1.
Okay, so up 1.
And then the negative 2 would be right 2 units.
Right 2.
And then the negative sign in front of the parentheses would be a reflection.
Yep, reflect over x-axis, right? So again, take care of that reflection first, then do your translations here, okay? So since I know I'm going right 2 and up 1, I'm going to kind of like focus more on the first quadrant there because the vertex originally was at 0, 0. It's going to go right 2 and up 1. So again, I'm just going to kind of do something like that and show, okay, so we moved right 2 and up 1. There's where my new vertex is going to be. Okay, but reflection over the x-axis, that means instead of being a nice smiley face, we're going to have a frowny face. Womp, womp. Okay, like that. And again, if you want to be more precise here, that's fine. You can, use a t-chart and stuff like that. You know, make a little chart and plug in some x's and get some matching y's. But really, again, just the sketch is what I'm most concerned about right now. Okay. By the way, what would the domain for this be? Negative infinity to positive infinity, right? We're going to hit all the x values there. So yeah, negative infinity to infinity. That's right. Will the range be negative infinity to infinity? No. What will the range be then? Negative infinity to 1. Okay. Is it okay to write? Is it okay to write this? No, it's not. Okay. Your intervals should start from the left, being the least or the smaller number, to the right, being the higher number. Okay. So I can see why you might think that, because we're kind of like starting at 1 and like going down to negative infinity. But you got to kind of like get rid of that thinking here. The range is describing, from the lowest point to highest point. So from the lowest is negative infinity, up to the highest 1. Okay. So this is incorrect. Okay. You will lose points if you write it that way. All right. So please don't. Please don't. All right. Be careful there. All right. So here's one for you guys to try, and then we'll get you started on your assignment here after that. Okay. So try this one. G of x equals x, absolute value of the quantity x plus 3 minus 3. Like that. Okay. So go ahead, try and sketch that real quick. And I will do the same. Okay, so something like that is what it should look like. Domain for this would be what? All our numbers, negative infinity to infinity, right? Range for this would be? -3 to infinity, right? Again, starting with that lowest number there, -3, it goes all the way up. Positive infinity, without bound. Okay, so that's that. Okay, your assignment is posted to the classroom, so you can get started on that here real quick if you like. All right, I suggest you do.